Alright, this is lab 4, which is oscillations. So a quick introduction. What is the problem? We're going to be comparing the oscillating periods of a computational model and a real-life example, along with discussing the energy changes involved and whether or not the energy principle will be satisfied. Why are we interested in this answer? It's going to help us better understand the energy principle and the forces that are involved in oscillation. So a quick summary of the results. This lab is going to show us how our computational model is much more accurate in the oscillation, and there are many potential errors when it comes to tracker in the video that we used, including the frame rate, whether or not it downloaded correctly, etc. It's also going to show us how the energy principle is going to be satisfied. So our fundamental principles. Our energy principle states that energy is neither created nor destroyed. So this means that total energy in this specific case will be equal to total kinetic energy plus gravitational potential energy plus spring potential energy. This is because there are springs involved. And so our kinetic energy is going to be 1/2 mv squared, our gravitational potential energy is mgh, and our spring potential energy is 1/2 ks squared. So for our forces, we're going to be using Newton's second law, which we all know is dp dt, the spring force, which is negative k, L minus LO, L hat, and gravity, which is just mg. So first I'm going to go ahead and show you the video that we used with Tracker, and you can see where a lot of these potential errors could come up when I play the video. So we have that ball oscillating back and forth. It's a really laggy circle, which means the frame rate was having a lot of issues. My computer was also probably having problems downloading all this stuff. But you can see these graphs being created and also the data right over here that we're going to be continuing to use. And let's get right back to it. So first we have our x versus time graph, which is just this oscillating graph right here. And we have our y versus time graph, which once again is this oscillating graph right here. So now for our code. So our ball, the mass of the ball is 0.402, so we went ahead and updated that, along with getting our position from the experimental data and the time as well, just starting at 0. And so down this way, we also have our spring constant, which we calculated, along with our gravity and our relaxed length, which again we calculated. Down here we have L is the position minus the string position. L hat is L divided by the magnitude of L. Up here it's a little bit cut off, but we have S as the magnitude of L minus L naught. And then down here we edited all of our energies to have the equations that I showed you earlier. And then these are our initial energies, this is our final time, this is our spring constant in L hat, and here is our gravity vector, our F net, the velocity update formula, the position update formula, again we have L hat over here, and then these are all of our energy changes. So we have delta U of gravitational energy, we have delta U of spring potential energy, we have our kinetic energy, we have our total energy, and our total change in energy. And these are just going to show how we plotted that. So I'm also going to go ahead and run that code for you. So we have to choose a CSV file. This is the file from the experimental data that I used. So again, you can just see it kind of oscillating. You see these graphs forming with the change in energy versus time, the x position versus time, and the y position versus time. And so going back to our slideshow. So here we have the change in energy versus time, which we can kind of analyze. We have the change in potential energy of the spring in this green right here. We have the potential energy of the gravity right over here. And you see how this makes sense because that spring is vertical. So these are going to be canceling each other out. And then we have our kinetic energy, which is oscillating very small. You can barely see it right over here on this 0 line. And this is our total energy is this orange line right here, which you can see is right on the axis. So this is our x position versus time. So our model didn't have any changes in the x position, which obviously again is due to the error from the videos. And then we have our y position versus time. Once again, the discrepancies are due to the error in the video. And what does it mean? So is the energy principle satisfied in this case? Yes, the energy principle is indeed satisfied because you can see that total energy never leaves the axis. This is making it 0, so energy is neither created nor destroyed. The energies are constantly canceled out by each other. So what does it mean? So we went ahead and we calculated the oscillations. As you can see, there is a pretty big discrepancy between the x oscillation and the y oscillation that we calculated. And this is, again, where it's causing some of these errors where the graphs look incorrect. So, in conclusion, the energy principle is always satisfied in these correct models, and the computational model is much more accurate than our experiment. These different oscillation periods are going to cause major discrepancies, but once again, our energy principle is always satisfied, and through this lab, we have learned more about the forces on an oscillating object. Thank you so much for watching.